Hi, my name is Quirijn, and in this Bits of Q tutorial I'll explain all you need to know about lambdas, which follow this strange syntax with all the different parentheses and brackets, so I'll be explaining exactly what this means, how it all works, and, most importantly, when you should be using them to improve your code. Let's get started. First, a bit of a motivational example. Say I have a vector of customers. For every customer I have a name and the number of purchases they made. Now I want to sort this vector based on the number of purchases. So I include my algorithms header and to start writing out a sort statement. I pass it the begin and end iterators to this vector, and then as a third argument, I get to tell it how it should compare to customers. In this case, I want it to compare based on the number of purchases. And there are several different things I can pass here. We'll start by looking at the options that were available before we got C+11, and afterwards we see how lambdas can be used instead and what their advantages are. For a simple comparison function like this, you can simply pass a free function. For example, this less purchases function, which takes two customers and compares them based on their number of purchases. The function will be passed as a function pointer, and the sort function will invoke it whenever it needs to compare customers. If your comparison operator gets a bit more complicated, you might want to consider calling a so-called functor instead. A functor is nothing more than a class that acts like a function. In other words, it implements a call operator. Here you'd probably want to accept two customers again by reference to const, but because I have limited space on my slides, I'm just accepting them by value here. To use this customer compare functor for our sort, we first need to create an instance of it. We can then pass this instance, the comp object in this example, to the sort function instead of the free function we had before. One of the advantages of using a functor instead of a free function is that you can now add some state to your comparison class. We could, for example, have a single customer compare class that behaves differently based on the user configuration. We might, for example, change what it uses to make the comparison. In this case, it could either compare based on customer name or number of purchases. If we accept this compare by enum in our constructor, we can pass the desired behavior upon constructing the class. As you can see, this offers a lot more flexibility, but at the same time it has the disadvantage that we're adding a lot of boilerplate to make this all work. This is one of the reasons why in C+11 lambdas were introduced as an alternative. With lambdas we can simply replace all this code with something like this. So, what's happening here? First, let me emphasize that using a lambda like this is exactly the same as creating a functor class and then passing that to your sort function. It is purely syntactic sugar, so we don't have to write so much boilerplate. So let's have a close look at the syntax. Every lambda starts with two square brackets, and in those brackets you can specify what's called the capture. The capture essentially specifies the member variables of the functor and what the constructor should accept as parameters. We'll go into more detail on this later. Next, in normal parentheses, we have the function parameters. Lastly, in braces, we have the implementation of our lambda. As I said before, lambdas are just syntactic sugar for classes with a call operator. So to understand how this lambda definition is mapped to such a class, let's have a look at what the compiler generates from it. First of all, the name of the class that will be generated by the compiler is compiler defined and is not something we can rely on. Secondly, it generates a call operator that's always const. This is important to remember. Even though we never specified the const keyword in our lambda definition, the call operator for lambda is const by default. As a matter of fact, the call operator is not just const, it is even automatically marked as a const expression since C+17 if the compiler deduces that this is possible given the implementation. As this depends on the implementation, and also because I have limited space on these slides, I'll be omitting the const expr keyword when showing generated lambda classes from now on. It's just something to keep in mind if you ever want to use lambdas for any compile time coding. The parameters and implementation of the call operator are exactly the same as specified in our lambda. As for the private members of this class, they are determined by the capture. We used so-called init capture in this example, which takes the form of a comma-separated list of assignments. When determining the type for the local config member, auto-type deduction is used. Aside from this assignment style init capture, which was introduced only in C+14, we can also specify a variable directly in the capture class. When capturing like this, a copy will be made of the config variable defined in the scope where the lambda is defined, and it will be assigned to a local config member variable of the generated class. The type of the member variable will be the exact same as the declared type of the captured variable. It even includes const and volatile qualifiers, should they be present. If you are interested in the intricacies of type deduction, both when using lambdas and in other contexts, I recently released a 2-part tutorial where I go into detail on all the different forms of type deduction in C++. I'll leave a link in the description. Sometimes you want to capture something, but you don't want to create a copy of the object, especially if you're dealing with big objects that are expensive to copy. In that case, you can add an ampersand to capture by reference. Capturing by reference works both for these normal C++11 style captures, as well as for the assignment style lambda init captures that we saw before. As your lambdas get more complex and you need multiple captures, your code can easily get a bit cluttered. Therefore, 2 shorthands were introduced for simply capturing everything needed in the body of the lambda and otherwise not available. You can use the equals sign to capture copies of everything. I simply remember this as equals means assignment in C++, and in C++ an assignment is a copy by default. Similarly, you can also use an ampersand to capture everything by reference. In general, when deciding to capture by reference or by copy, a good rule of thumb is capture by reference when passing down, like in our sort example where we are passing a lambda to another function, and capture by copy when passing up or storing your lambda for later use. The reason you should generally copy in this case is that you don't run the risk of having a dangling reference if the original gets destroyed. When you pass down to, for example, the standard sort algorithm, you know exactly what the lifetime of your lambda will be, and hence capturing by reference is safe, and often leads to faster code when big objects are captured. Now, let's have a look at a different kind of lambda. Since lambdas make it easy for us to add some state to a function, you could try to implement a simple counter lambda that returns the next integer every time it's called. However, if I would try to call such a lambda, I would get a compilation error. GCC will say something like this: error, increment of read-only variable I. Klang's error is a bit more descriptive, although it does use a bit of jargon. Error, cannot assign to a variable captured by copy in a non-mutable lambda. To understand what's happening here, let's again consider the class that is generated by the compiler when it sees this lambda. Remember how I emphasized that the call operator is const by default? That's why, even though the type for I is deduced as a normal, non-const integer, in the context of this call operator, I is const and hence it cannot be incremented. We can prevent the call operator from being marked as const by adding the mutable keyword to a lambda. The last type of lambdas I want to discuss are the so-called generic lambdas. These lambdas take their parameter using the auto keyword. If we look at the class that is generated for such a lambda, we see that generic lambdas are just normal classes where the call operator is a template under the hood. Just like with the class name, we have no control over the name of the template type. Since these generic lambdas are just templates in disguise, we can also use a double ampersand to accept our inputs as a forwarding reference. We can then perfectly forward our inputs using standard forward. Of course, to do so, we need to know the type of our input parameter. Normally you would just put the template parameter here, but as this is generated, we don't know the name of it. The simplest solution is to use decltype to find the type of our parameter. For more information on forwarding, what is really happening in this standard forward statement, and what its advantages are, check out the video I made on perfect forwarding. Link is in the description. Starting with C+20, we have an alternative to using decltype. We can actually create template lambdas where we specify the template parameters ourselves. To create a template lambda, you use the familiar angular bracket syntax after the capture specification. I promised this was the last bit of lambda syntax I would introduce, so let's now have a look at the body of a lambda, and in particular the meaning of the this keyword. I have a new lambda here, defined in the foo function of a class C. In the lambda I use the this keyword to call the bar function. This works differently when used in lambdas. In lambdas, this refers to the outer scope where the lambda was declared, not to the generated lambda class. Although at first this might sound a bit weird, why would this mean something different in a lambda? It's actually quite convenient, as it allows you to refactor a long function using lambdas without having to worry about it suddenly meaning something different. Okay, that's all I wanted to tell about creating lambdas. Now let's have a look at how we can pass lambdas around and how to store them. A simple way to create a function that accepts a lambda is to make it a template. As lambdas are simply instances of a class, we can pass them around using templates. Here, the run async function accepts an input f by forwarding reference. An advantage of using a template to specify the type of f is that we can now not just deal with lambdas, but with anything that's callable. The standard library uses this same approach. That's why we could pass both a free function, a functor, as well as a lambda to the standard sort function. Alternatively, as lambdas are just callable objects, they can also be assigned to a standard function. This allows us to both enforce a certain signature, like a function accepting int and returning void, as well as store them for later use. This is especially useful when writing asynchronous or event-driven code. Do be careful when capturing by reference if you are storing your lambda for later use, as you might end up with a dangling reference. When in doubt, it's safer to capture by copy if you're going to use your lambda later. Let's summarize what we have discussed. A lambda consists of a capture, if you're using C+20, optionally some template parameters, function parameters, and a body to hold the implementation. This is all just syntactic sugar, as underwater the compiler will simply generate a class with a call operator. The capture is what determines the member variables of this class. There are many ways of specifying your capture, but they roughly fall in two categories. Either you're capturing by reference or you're capturing by copy. The call operator of the generated class is const by default. If you need to modify your members, you can add the mutable keyword to generate a non-const call operator. When using the dis keyword in a lambda, you're actually referring to the dis defined in the outer scope, not the generated lambda class. As lambdas are simply objects, we can use templates to accept lambdas as parameters for our functions. This has the additional advantage that we can accept anything that's callable. And lastly, if you want to store your lambda or simply enforce a certain signature, you can easily do this using the standard function. That's it for this episode. I hope you enjoyed and learned something new. If you did, make sure to like and subscribe for more. See you next time.